Last time, we solved our Midwestern road trip problem and found the shortest loop by using brute force. But we also learned that brute force only works when the number of cities is tiny. So here's the real question. How do delivery companies, airlines, or GPS apps actually solve these problems when brute force is impossible? Most experts actually believe that no efficient method that guarantees the perfect shortest route for the traveling salesman problem will ever be found. In fact, the Clay Mathematics Institute literally put a $1 million bounty on the solution. We'll get into why later, but for now, let's look at what people actually do in practice. Heuristic algorithms, aka quick and dirty methods, are shortcut strategies that don't guarantee perfection but give pretty good results really quickly. One example of this is the nearest neighbor algorithm. We'll use the same example from last time, starting at Chicago. Then we'll go to the closest unvisited city. Repeat until everything's been hit, then return home. It's fast, it's simple. We know this isn't optimal, but it's better than many other solutions. Let's look at another algorithm, the sorted edges algorithm. List every connection between cities and sort them from shortest to longest. Then keep adding the smallest edges as long as you don't form a premature loop or overload a city with 3 roads. Also fast, usually decent, but still not always perfect. These aren't correct algorithms, they're just ways that people have come up with to get by. They embody a core idea in computer science. Sometimes getting the perfect example is too expensive, so we have to settle for good enough. And that brings us to one of the greatest unanswered questions in all of math and computer science, P versus NP. P problems, or polynomial time problems, are problems that are easy to solve quickly with a computer, like multiplication, sorting a list, or checking if a number is prime. NP problems, aka non-deterministic polynomial time, are easy to check if someone gives you a solution, but brutally hard to find the solution from scratch, like Sudoku, scheduling, and our friend the traveling salesman problem. It can be difficult to solve a 9x9 Sudoku puzzle, but if you're given the solution, you can easily verify that it's correct. This is the same case for computer, but what if the size of the Sudoku board increases? It's still relatively easy to check the solution, but the time needed to solve it increases exponentially. All P problems are NP, but here's the million-dollar, actual literal million-dollar question. Are P and NP secretly the same? In other words, if it's easy to check a solution, does that mean it should also be easy to find one? Does P equals NP is one of the 6 unsolved millennium problems presented by the Clay Mathematics Institute with a $1 million reward for its solution. So what would happen if P equals NP? The traveling salesman problem would be solved, global delivery routes are optimized, and billions of dollars are saved. Complex logistics, circuit design, and scheduling would be trivial. Protein folding, one of the biggest challenges in medicine and drug design, is also an NP problem. That means that we could find cures for diseases like cancer dramatically faster. And beyond practicality, there's a philosophical impact. MIT computer scientist Scott Aaronson put it best. If P equals NP, everyone who appreciates a symphony would be Mozart. Everyone who can recognize a step-by-step argument would be Gauss. Solving something would be no harder than recognizing a good solution. Creativity itself could be algorithmic. There's way more depth to this, subclasses like NP complete, NP hard, co-NP, and that is a wonderful rabbit hole to fall down sometime. Here are some great resources I'd recommend that sucked me down the rabbit hole. Thanks for watching, and stick around for even more cool math stuff.